Hello, chemists. It's Jolly again. This discussion is going to be on radicals and their reactions. So I'm going to go over to the handout. Now, there's not going to be very many of them, so it's a short discussion, but they're important. All right, we're going to talk about them and their two types. So the first one is the reaction with a carbon-hydrogen bond, and that's often called hydrogen extraction. And we're going to see it in two cases. We're going to see it with the halogenation of alkanes and the allylic halogenation. And generically, it means rip off a hydrogen. So if I have, and this happens to be ethane, one hydrogen and I have a halogen, it's going to rip that hydrogen off, leave a radical behind. Okay, so generic extraction. The other one is going to be reacting with a carbon-carbon double bond in an addition. And just like we've seen in the past, every time you break a pi bond, you have to put two things in its place. But we have to decide, do I want to put the radical there, or do I want to put the radical there? Again, this one is secondary, this one is primary, so we would not form the primary. And then we would go on, and there's another radical somewhere that would go on and make the product. All right, those are the two generics. Let's talk about the specifics. All right, so this is a carbon-hydrogen reaction. This is the alkanes with the halogens. Now, of course, we could use all of the halogens except iodine, is feeling pretty lazy and it's not very reactive in this reaction, where fluorine, on the other hand, is a little overactive and it loves to react. In fact, it's so reactive, it can be explosive, and there's absolutely no selectivity. Fluorine is also extremely reactive with no selectivity, but hopefully it doesn't blow up in our faces. Haha. So no fluorine for us. That's a world by itself, but we can use chlorine. Now, both of these, they're not selective, so they don't distinguish between tertiaries, secondaries, primaries. They just react to first give the monohalos, but don't forget, once you put a group on, it could activate it, and so we could get polyhalos as well. Now, bromine is a little bit less reactive, so therefore it's more stable, but you could go on and still make polys. All right, these are substitution reactions, and after the first step, okay, which is initiation, the first step in the overall reaction is hydrogen extraction. And if we were to make stereocenters, if we only made one, we would get a racemic mix because radicals are sp2 hybridized and they're flat. If we make more than one stereocenter, we're going to have to figure out what ratios. Okay, we're going to get all the products, but we will not end up with racemic mixes. And that's a little more detailed than what our discussion needs, so we just won't make more than one stereocenter. All right, so we need to talk about chlorine and bromine. Let's do chlorine first. All right, if we have the propane molecule, there are two unique types of hydrogens that the chlorine could go after. All right, the first step, of course, is initiation. And then my chlorine radical can rip off that one or that one. So let's look at our two possibilities. We could have this, and we could have that. All right, this one is secondary, this one is primary, but chlorine is not selective, so it's going to create both of those. And then there are still more chlorine radicals floating around, and it is going to terminate and attach to the carbon chain. Now, those are the mono products, but don't forget, it can go on and create poly. So when you're doing these reactions, you are more than welcome to write the word poly. But for chlorine, you're going to show me all of the possibilities. And then plus poly. Now, I've told you in the past, if you ever make more than one of the same functional group, you need to tell me which is major and which is minor. That is a little bit more difficult in reactions like this because we need to talk about something called kinetic control versus thermodynamic control. In a nutshell, kinetic control is based on the rate, which is based on the activation energy. So whoever has the lowest activation energy will form first, and that is called the kinetic product. The thermodynamic product, luckily, is the same as we've been studying all along. So thermo is based on stability. Now, should I label the major product as the most stable product, or should I label it as the first one that it can see? We're going to leave that for a different discussion. But for the halogenation of the alkanes by chlorine, you're going to show me all of the monochlorine, and then you're going to show me, hey, yes, we could still do poly. I'm going to jump over to the whiteboard to show you bromine. Now, bromine, on the other hand, is a little bit more selective. So it's going to go after the most stable hydrogen. Whoops, that's a bromine. So it's going to go after the hydrogen that will make the most stable radical. And in this case, secondary is the best we can do. And so initiation, hydrogen extraction, and we're going to end up with that one with another bromine radical. And the termination step. All right, so there is the most stable product from the bromine, but there is a chance of still going on, so I like to put plus poly. So for chlorine, you would give me all possibilities plus poly, and for bromine, you would only give me the most stable plus poly. All right, that takes care of halogenation of our alkanes. What about our allylic carbons? All right, so when I say allylic, remember that means one away from a double bond or a pi bond. All right, so that is the allylic location. Why is it so special? Well, because it has resonance stabilization. If you ever go through an intermediate, look out for rearrangement and look out for resonance. Now, we know radicals don't rearrange, but we do have to look out for resonance. So I need to be careful when I make radicals in the allylic location. Okay, we do know allylic radicals are more stable than tertiary. We saw that using the bond dissociation energy. So we need somebody that is going to give us just enough bromine to react, but not so much that it's going to go crazy on us. And that molecule is called NBS. So basically, when you see NBS, okay, of course you have to have lighter heat or something, but you're seeing a bromine radical. And so if I take NBS and some kind of light heat, I'm ending up with a bromine radical, and it will go after the most stable location. So the hydrogen, when it comes off, that leaves the most stable radical, and it happens to be the allylic hydrogen. So I end up with this. Aha! But what are we going to do? This can go through resonance. In this case, it's the same molecule. But if you can go through resonance, you need to consider all the possibilities. Luckily, in this case, they're identical. There's more bromine going around here. So it's going to do its termination step right there. All right, I'm going to go to the whiteboard for the other two. One thing we need to be aware of, could this be done with diatomic bromine in heat? Yes, but you run the risk of just going through halogenation and a bromonium ion, okay? And whenever two different resonance structures can be drawn, two different allylic halides can be formed. So let's jump over to the whiteboard. All right, so we saw what the bromine would do there. Let's take this molecule. It's my favorite molecule as an example. Okay, so we've got NBS. You know what? Let's be crazy and put a little heat this time. All right, so basically that is this one. Now it's looking for allylic hydrogens, or specifically, it's looking for hydrogens that will give it the most stable radical after it leaves. So I have this hydrogen and I have that hydrogen. That's identical. Okay, so there's two unique kinds of hydrogens that it could rip off. So if I take this one versus this one, let's take a look at the two possibilities. There's one, and there's two. Anytime you go through an intermediate, look out for rearrangement and resonance. In this case, I can do resonance. So that one also makes that one. And this one also makes that one. So I actually have four different types of intermediates. I'm going to have to show products from all of them, but of course I'm going to make more than one of the same type of functional group. So I am going to discuss which ones are major and which ones are minor. Now I put arrows on that. So I'm going to just redraw those down here. And all right, so there's my four possibilities. Let's talk about their stability first. All right, so this one, yes, it's allylic. Okay, so it's secondary, it's allylic, but that's not the only thing that contributes to stability. This also has a mono substituted alkene. All right, and I said secondary, that is a tertiary. All right, so I've got tertiary, allylic, and monosubstituted. I have got secondary allylic and disubstituted, geminal. I have primary allylic and trisubstituted, and I have primary allylic and also trisubstituted. All right, I'm going to tell you right now that when you're dealing with allylic, this is not really your first consideration. Okay, so it's not a tertiary, secondary, primary issue. It's an allylic, 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 and allylic. Now, this tertiary allylic is very tempting, but remember, it's not the only issue. So, as far as the alkenes are concerned, this is the most stable alkene, and it's also allylic. So, one of these two are probably the major intermediate that will go to the major product. So again, I have another bromine and I'm going to attach it to each of those. Too many right there. Okay, those are my four possible products. They are all alkenes, and then I would narrow it to these two to be the major product. And could I nitpick and go further? This one has less steric hindrance because the bromine is off by itself. So if I had to choose one, it would be that one as the major product, but I wouldn't cry if they were, pretty close in mixtures. And that is how we look at allylic bromination. What happens if I'm going to make a simple molecule this time. What if I use diatomic bromine with light or heat? Okay, now, as soon as we see that light, we want to do a radical mechanism, and the answer is yes. It will do allylic halogenation. But don't forget, it will also do old-fashioned addition and give us the bromonium ion. And the key is that would be in competition with our radical pathway. And why risk that? So generally, we do not use diatomic bromine in heat if we're trying to do allylic radical reactions. But technically, could it give you product? Yes, but it's not the best bet. NBS would be better. All right, those were our two carbon-hydrogen reactions. Okay. Whoops, that's supposed to say CC. All right, let's look at our carbon-carbon double bond. All right, HF, HCl, and HI are pretty much unreactive. So the only one that's going to happen is HBr. We are going to get the anti-Markovnikov product if peroxides are present, and we're going to get the Markovnikov product if there are no. Okay, so this is just plain old addition. That's not radical chemistry. That's what we learned before. All right, it is an addition. And if there is stereochemistry involved, if one stereocenter is formed, products are mixtures. And if more than one stereocenter, you get them all, but it's not a racemic mix. All right, let's do our simple molecule here. Okay, and then we're going to have some peroxides and some lighter heat. The first reaction in this case is, of course, going to break the weakest bond, and that is the peroxide bond. So we're going to make two peroxide radicals. It's going to react with the HBr. It's going to do a little hydrogen extraction action there. And so now we finally have a bromine. All right, that bromine is going to attack and break that pi bond. Anytime you break a pi bond, you can put two things in its place. So we're going to go to the most stable. Oh, look. I didn't violate any stability rules. The most stable radical happens to be in the Markovnikov location, so the bromine went in the anti. So by doing this reaction, I'm not violating stability rules. I'm just using the reactions to my benefit. And then, of course, there's some HBr. And I create the anti-Markovnikov halogen. This is still called hydrohalogenation. It just happens to go through a radical mechanism. So it's radical hydrohalogenation. All right, down here, I kind of give you an example of each kind so that you can play with those. But in a nutshell, quick review. All right, what did we learn? Just radical halogenation. Okay, radical halogenation. Chlorine is not selective, so it gives you all possibilities. So however many unique hydrogens there are, you're going to show me those products. And don't forget, you can get poly products from it. Well, we also saw diatomic bromine. It is selective, so you're only going to show me the stability ones, the most stable. But there is still the chance of going further and making polys. This is also radical halogenation. And then we saw the same thing with NBS, and then some kind of light or heat, and Br2, but with heat. With NBS, it is selective to the allylic location. Okay, so this is technically radical halogenation still. But beware, look out for resonance. All right, what about the bromine with the heat? This one, yes, can also give you that one, but you also run the risk of, remember, going through that would give you anti, and I think I put too many hydrocarbons. 1, 2, 3. Yep, I did. Would also give you anti-addition, putting 2 bromines on. So yes, it will work, not the greatest. All right, so there's our halogenations. And then we saw breaking pi bonds. If I had just done addition, okay, this one, the hydrogen goes on first. So the hydrogen would go right here. Whoops, not radical right there. So the hydrogen would go on first, and then the bromine would go on second. Okay, so that's Markovnikov. Hydro, halogenation. Okay, so that's what we saw before. The bromine goes on second. So if we want to get around that, we're going to use radicals. And in order to do that, you have to have the peroxide with some kind of lighter heat. And in this case, remember, this breaks. It makes the bromine. All right, it's going to go for this hydrogen or this pi bond. Now, we've already seen how it goes for the hydrogen. So is there a chance it would still go for the hydrogen? Yes, but the pi bond can be broken, and still with stability rules, I'm going to make the most stable radical, and here's the difference. The bromine goes on first, and then the hydrogen is added. And that's how you get the anti-Markovnikov. So still called hydrohalogenation, but this one is radical hydrohalogenation, and therefore it goes on anti-Markovnikov style. All right, that is our reactions for our radicals. Until next time, jolly out.